Okay, so the next speaker is Emanuele Venieri about Monte Cimone V2 down the road of RISC-V high performance computers.
So, hello everyone. So I'm here to present our project called Monte Cimone V2. For those of you who may be wondering, that shape at the bottom of the slides is Monte Cimone, the highest peak in Emilia-Romagna region, where Bologna is. And since we're from Bologna, we call our system Monte Cimone. So, in this presentation, I will talk about RISC-V and HPC. I will show you how Monte Cimone evolved over time, and how we did some performance evaluation, including also blast vectorization. At the end, I will show, obviously, the results of our work. So, first of all, for an HPC compute node, what do we need? What are the requirements for a compute node? Surely an high core count, possibly if we talk about CPUs, vector or matrix extensions, large amount of system memories to accommodate large datasets of models, PCIe supports, for example, to include accelerators, we talked about them before, or network cards, fast storage. From a software perspective, we expect operating system, job schedulers to manage various workloads in a big system, a monitoring system, and the packages and libraries. So, in the previous days, we saw how RISC-V is mature in the embedded domain, but in HPC, how is it going? Over the years, vector extensions were ratified. So we had a first draft, like the 0.7.1, and finally we got the ratified 1.0. Last year was ratified the RVA23 profile that targets server applications also. In the following years, we expect to receive also matrix extensions like AME or IME. Our journey with Monte Cimone starts with the C5 Freedom U740. This is the first example of a RISC-V PC based around 4-core SoCs implementing RV64GC. E4 built a server blade around this system, including 2 of these systems. And we took them to build Monte Cimone V1, the first at the time RISC-V cluster, the first in the world, let's say. And it features 4 E4 blades, for a total of 32 cores and 128 gigs of distributed system memory. The scope of this project was to see if it was feasible to build a cluster around available RISC-V hardware, and building an actual cluster usable with a login node, job scheduling, and monitoring systems. Over the years, new hardware became available, like the SG2042. So this was the first example of a server class platform, a 64-core processor with vector extensions that implements the draft 0.7.1. This is featured in a couple of machines. The first one is the Milk5 Pioneer Box, that is a single-socket machine with 128 gigs of RAM, and in the E4 dual-socket server that features 2 of the processors and 266 gigabytes of RAM. We used this hardware to build Monte Cimone V2, an updated version that features vector extensions. So, starting from the first version of Monte Cimone, we had the C5 nodes, the login nodes. We added a new Slurm partition to accommodate the 3 Milk5s and 1 dual-socket server. We're planning also to expand it with more dual-socket machines, so stay tuned on that. So the cluster is based, as the first version, around Slurm. We have Hexamon as monitoring system. We feature a shared network file system. And we manage packages and libraries with SPAC. In Monte Cimone V2, we added 2 compilers to support the vector extensions of the new processor. So the Schwantig toolchain that is vendor provided, it is a custom version of GCC. And also GCC 14, that is the first version of GCC that supports the 0.7.1 RVV implementation of the SG2042, calling it TED vector. With it, we added some BLAS libraries. First of all, the OpenBLAS, both vanilla with no RVV and the vendor optimized with RVV, and also Bliss. Bliss is a BLAS framework that, for which we propose some optimized kernels. So, Monte Cimone V1 was evaluated with Stream, a memory benchmark, and HPL, floating point 64-bit compute evaluation benchmark. And after the introduction of the SG2042, we saw how it was also made available the Schwantig toolchain, the OpenBLAS, and we could use this to build a baseline, a performance reference for this kind of machines. So we used Stream and HPL with the optimized OpenBLAS, also to compare against the older version of Monte Cimone. In the meantime, Bliss made available some RVV 1.0 kernels, and with GCC 14 we could do a porting of it and some optimization, and I will explain that later. So, some results. Stream, memory bandwidth. So, we can see that across the 4 kernels of Stream, we have a performance improvement over the original nodes of Monte Cimone of around from 30 to 40 times, while the dual socket node performs over doubles that. So it is a big improvement. Then on single node HPL results, we tested both vanilla OpenBLAS, the green bars, and optimized OpenBLAS, the orange bars. Don't get fooled by the logarithmic scale. So you can see how the vectorization improves a lot the performances. So if we go across multi-core runs, we can see how the performance scales. And actually, we found that increasing the core count of workloads, we have a decrease in performance attainable with respect to the theoretical peak. That is the line that I highlighted. And this is valid also for vanilla OpenBLAS. At the end, we concluded that, also Nick anticipated it, that this machine has a quite big bottleneck on the memory subsystem. So we hope in future revisions. Instead, for multi-node results and also a comparison with the Monte Cimone V1, this is a comprehensive vision of the results. So, first of all, we have that a single node of Monte Cimone V2, a single socket, so a MILC5, outperforms the full cluster, the full Monte Cimone V1 by 10 times. So this is a very big improvement. Then another thing that we notice is that we scale so much in performance that linear scaling across nodes in multi-nodes runs is not possible anymore. So if in Monte Cimone V1 we had a linear scaling across multi-node runs, in Monte Cimone V2 we cannot. And this is also demonstrated by using the dual socket server. So with the same number of cores, but with a different communication between them, so an Ethernet link versus onboard communication, because it's a dual socket system, we achieve a performance that is really higher. And so this is a note for future development in HPC systems, where maybe in RISC-V we want to use something like InfiniBand or, in general, low latency interfaces. Going on with the Bliss optimization. So I said before that Bliss comes with some RVV1 microkernels. So the execution is split in microkernels over little tiles of matrices. And what we first did was to adapt the version that is used in the assembly code. So we did a porting from RV1.0 to 0.7.1, and we compiled it with GCC14 with the XT vector target. The vectorization strategy of Bliss is using single fuse multiply accumulate instructions on single vector registers. So in case of FP64 in SG2042 with 128-bit vector registers, every instruction uses 2 values. What we found is that this implementation performs like half of the optimized Open Blast, so it was quite low. And we tried to leverage register grouping. So to elaborate the same amount of data, we use a single instruction. And so these are the results. The blue bars are actually the numbers from the Open Blast of before. And the yellow one are the original Bliss vector implementation. You can see that there's quite a discrepancy. But after our optimization, so what we obtain a 49% improvement in the dual socket, and performance that is on par with the vendor optimized Open Blast. This shows also the effectiveness of register grouping in this type of microarchitecture. So, to conclude, Monte Cimone V1 versus V2 showed how the RISC-V ecosystem is rapidly evolving. And if we check the top 500, we see that in 2 years, we have seen a performance improvement that in average is obtained in 8 years. So for the RISC-V community, I think that this is a very good result. And the Bliss library optimization showed how we could obtain much higher performances over the original version of this library, obtaining on-par performance with vendor-optimized libraries, and also we committed it to the public repository of Bliss. So you can check on it on GitHub if you want. And so that's all. Thank you for your attention.
Thank you.